Welcome back to the deep dive. Today we're tackling a topic that sounds a bit negative at first glance. Electrical resistance. You hear resistance and you probably think of something blocking the way, an obstacle, right? Something getting in the way. But maybe that's not the whole picture. Yeah, we really want to challenge that first impression today because honestly, electrical resistance isn't always the bad guy. Sometimes it's actually, well, essential, crucial for safety, for things working right.
It's actually a bit like bacteria, you know?
Bacteria? How so?
Well, when you first hear bacteria, you probably think, oh, illness, germs, bad stuff. But then you learn there's harmful bacteria, sure, what we might call euhygien. But our bodies also rely heavily on beneficial bacteria, euhygien, for things like digestion. They make stuff we absolutely need.
Okay, I see the parallel. So resistance can be good or bad depending on the situation. That's a really neat way to put it. So our mission today really is to break this down simply, especially if you're maybe newer to some of these electrical concepts. We want to explore why different types of resistance matter.
Exactly. We'll look at four main types: specific resistance, insulation resistance, contact resistance, and grounding resistance. Understanding what each one does is the key. Why sometimes you want it low, and sometimes, surprisingly, you want it high.
Okay, let's dive right in then. First up, specific resistance, or goyujyohang. What does it mean for a material to have its own resistance?
Right. It's like an inherent property of the material itself. Its natural tendency to impede electrical flow. It's defined by what the material is made of, its temperature, and importantly, its physical dimensions, how long it is and how thick its cross-sectional area. We usually measure it for a standard size, like 1 meter of length and 1 square millimeter of area. That gives you a baseline for that specific material.
Okay.
And the key thing to grasp is the relationship. For the same material, make it longer, and the resistance goes up. Make the cross-sectional area smaller, like a thinner wire, and the resistance also goes up.
Right, like trying to push water through a pipe. A longer, narrower pipe offers more resistance. Makes sense.
Exactly that analogy, and engineers use this constantly. If you're sending power miles away, you can't use a tiny wire. The specific resistance over that length would just waste tons of energy as heat. That's why power lines are often so thick.
Gotcha. And it has a symbol, right? That Greek letter, rho.
Yep.
Rho.
And the unit is ohm meter, rho. It tells you how resistive the substance is, fundamentally.
So practically then, if you want electricity to flow easily, like in a wire, you want a material with low specific resistance.
Precisely.
And that's why copper is everywhere in wiring. It's a good compromise between low resistance and, well, cost.
Exactly. It hits that sweet spot really well. Good conductivity without breaking the bank.
Okay, so low specific resistance helps electricity move. But what about when we want to stop it from moving where it shouldn't? That brings us to the next type, where maybe higher is better. Insulation resistance, Jillianjiahang. Why do wires have that coating?
Yes. This is where resistance becomes our friend, our protector, really. Insulation is fundamentally about not conducting electricity. So insulation resistance measures how good a material is at stopping that flow. We test it by applying voltage and seeing how much current manages to sort of leak through or across the surface.
Okay.
So inside the wire, the copper needs low resistance, like we said, but the coating, the insulation around it, that needs super high insulation resistance. That's what stops the electricity from jumping out and giving you a shock if you touch it. It's absolutely vital for safety.
And if that insulation fails, that's insulation breakdown. That sounds bad.
It is bad. Very bad.
I guess you see that when connecting wires, right? If you strip too much insulation off, you expose the copper.
You've created a path, yeah.
Yeah.
A weak point.
And that's why we wrap it tightly with electrical tape to basically rebuild that insulation layer.
Exactly. You're restoring the insulation performance. And we actually measure this. There are tools, insulation resistance testers, often called MEGRs, just for checking this. If the reading is too low, meaning the insulation is poor, that wire or piece of equipment is dangerous. Risk of shock, risk of leakage current, Nugent, shouldn't be used.
So higher is definitely better here.
Always higher. For new installations, you want it over 1 megaplorn, typically. Even for routine checks, it should stay above half a megaplorn. These aren't just numbers, they're safety thresholds.
Makes total sense. Okay, moving on. What about contact resistance, Japchak Jehang? This sounds like something we bump into daily, like a loose phone charger.
That's a perfect example, yeah. Contact resistance happens right at the point where two conductive things touch, and electricity tries to cross from one to the other. Its value isn't fixed. It depends on the materials touching, how hard they're pressed together, and how much current is flowing.
And when it's wrong, like that loose charger plug or maybe wires not connected tightly, That's when things don't work. Or worse, you get sparks.
Exactly. If the connection isn't solid, the contact resistance can be too high. This blocks the current flow, generates heat, can even be a fire hazard.
So for things that should be connected, we want low contact resistance.
Absolutely. You want a smooth, easy path for the current between them.
And we actively try to reduce it.
We do. Pushing a plug firmly into the socket, you're increasing the contact area and pressure, reducing resistance.
Ah.
Or think about computer connectors, like for monitors. The pins are often plated with gold or similar metals. That's not just for looks. It prevents corrosion and keeps contact resistance low and stable over time.
Right. Prevents that fleeky connection.
And soldering. In electronics, when you melt solder between two components, you're essentially creating a much larger, solid bridge for the current, drastically lowering the contact resistance.
Clever. These are great examples. Okay, one more type. Grounding resistance. Jiaptajeohang. This sounds very safety-focused.
It is, absolutely. Grounding, or jiapji, is purely a safety measure. The whole idea is to provide a safe path for any dangerous leakage current to flow directly into the earth, Deji. So grounding resistance is simply the resistance between the grounding electrode, that metal rod or plate buried in the ground, and the earth itself.
And what makes it good or bad?
For this one, lower is always better. A low grounding resistance means there's a really good, easy connection to the earth. If there's a fault, like a wire touching a metal casing, the current will rush down that grounding path instead of through someone who touches the appliance.
So just like specific resistance for conductors and contact resistance between connections, we want grounding resistance to be as low as possible for safety.
Exactly. That's why electrical codes have strict limits on how high grounding resistance is allowed to be. It has to be kept low to be effective.
Wow, okay. So we've journeyed through 4 different phases of resistance. Specific, insulation, contact, and grounding. Quite a spectrum.
It really is. And I think the big takeaway, hopefully, is that resistance isn't just one thing. It's not inherently good or bad. Its role, and whether you want it high or low, totally depends on what it's doing in the circuit or system. It's about context. Managing these different resistances is, a huge part of electrical design and safety. It's about balancing conductivity where you need it with insulation where you don't, ensuring good connections and providing that crucial safety path to ground.
That's a really useful way to think about it. Context is everything, which makes you wonder, how often do we apply that simple good or bad label elsewhere? Maybe this idea that something seemingly negative can have vital, diverse roles depending on the situation applies to other things you encounter, other areas of knowledge, or even just everyday life.
Oh.
What else might benefit from a deeper, less judgmental look, a proper deep dive? Something to think about.